Ever wondered about the secret behind your computer's ability to run multiple applications smoothly, even when it doesn't have enough physical memory? Today, we're diving into the world of page replacement in operating systems. Page replacement is a fundamental mechanism in the management of virtual memory in operating systems. It's like the conductor of an orchestra, deciding which memory pages to swap out when a new page needs to be loaded into the random access memory, or RAM, but there is no free space available. An effective page replacement algorithm is like a master conductor, optimizing the performance of a system's memory by reducing the number of page faults and managing the limited physical memory efficiently. Now, let's take a step back. What is virtual memory? It's a clever trick that operating systems use to give the illusion of having more memory than is physically available. They store and retrieve data from secondary storage like a hard disk or SSD for use in RAM as needed. This process happens on a page-by-page basis. So what happens when a program accesses a page that is not currently in memory? A page fault occurs. This triggers the operating system to load that page from the disk. But what if all the memory frames are full? Well, the operating system must choose a page to remove to make room for the new page. The strategy used to select the page to be replaced is defined by the page replacement algorithm. In essence, the page replacement algorithm is the decision maker, the judge deciding which page gets to stay in memory and which one needs to take a trip to the disk. It's a balancing act, considering factors like the complexity of the implementation, the impact on performance, and the frequency of page faults. Understanding how the operating system decides which page to remove when the memory is full leads us to the fascinating world of page replacement algorithms. The simplest page replacement algorithm is FIFO, or first in, first out. As the name suggests, this algorithm operates on the principle that the first page that was brought into memory should be the first one to be swapped out. It's like a queue at a grocery store. The first customer in line is the first one to be served. However, simplicity comes with its own set of challenges. If you've ever heard of Bilady's anomaly, you'll know that it's a phenomenon associated with the FIFO algorithm. This anomaly occurs when increasing the number of frames in a system actually leads to an increase in the number of page faults. Imagine adding more cash registers at the grocery store, but seeing the queue of customers grow longer instead of shorter. It seems counterintuitive, right? This is one of the limitations of the FIFO algorithm. While FIFO is simple, it's not always the most efficient. That's why other, more sophisticated algorithms have been developed. Next up is the LRU, or least recently used algorithm. This approach is a bit more sophisticated than FIFO, and is based on the principle that the pages used most recently are likely to be used again soon. It's like your favorite book on a bookshelf. You're more likely to read it again than the one you haven't touched in years. Right? LRU operates by replacing the page that has not been used for the longest period of time. It's like removing the dustiest book from your shelf to make room for a new one. While this strategy can be highly effective, it comes with its own set of challenges. The implementation is more complex as it requires tracking the age of each page in memory, kind of like remembering when you last read each book on your shelf. LRU requires more computational resources, but it can deliver better performance than FIFO. Now, let's explore what's theoretically the best algorithm, the optimal page replacement, and a practical compromise, the clock algorithm. The optimal page replacement algorithm is an intriguing concept. It operates under the principle of replacing the page that won't be used for the longest time in the future. It's like having a crystal ball that can predict your program's future needs. This approach minimizes page faults and, in theory, offers the best possible performance. But here's the catch. It's practically impossible to implement in real-time systems. Why, you ask? This algorithm requires future knowledge of the reference string, which is typically not possible to predict. So while it's a fascinating concept and theoretically the best, its lack of practicality makes it more of a benchmark than a viable solution. Now, let's turn our attention to a more feasible solution, the clock algorithm. This is often used in real systems and offers an efficient compromise. It operates like a clock, hence the name, with pages arranged in a circular list. Each page is given a second chance before being replaced, making it a fairer system and reducing unnecessary page faults. If a page's reference bit is set, indicating it has been used recently, the bit is cleared. and the page is given a second chance and moved to the back of the queue. This approach ensures that frequently accessed pages are less likely to be replaced, leading to an overall reduction in page faults. However, like all algorithms, the clock algorithm is not without its limitations. It requires additional hardware to implement the reference bits and the circular list, and while it performs better than simpler algorithms, it doesn't quite reach the theoretical efficiency of the optimal page replacement algorithm. While the optimal algorithm is theoretically the best, its impracticality leads us to more realistic solutions like the clock algorithm. Another straightforward yet unpredictable algorithm is the random replacement. As the name suggests, this algorithm replaces a random page when the need arises. It's akin to pulling a name out of a hat or rolling a dice to determine which page gets swapped out. This method is remarkably simple to implement, requiring no tracking of page age or usage frequency. However, simplicity comes with a trade-off. Its random nature means it lacks the intelligence of other algorithms. It doesn't consider which pages might be needed soon or which ones have been idle for a while. It's a bit like blindly throwing darts and hoping for a bullseye. Consequently, the random replacement algorithm generally results in a higher number of page faults compared to more strategic algorithms. So, while it can be effective in certain scenarios, and its simplicity is certainly appealing, random replacement usually doesn't perform as well as its more sophisticated counterparts. Random replacement, while simple, generally performs worse than more strategic algorithms. The choice of a page replacement algorithm is not arbitrary. It significantly impacts the performance of an operating system. In the world of operating systems, the selection of a page replacement algorithm isn't a trivial matter. It's a decision that carries weight, capable of shaping the performance of a system, particularly when the system is under heavy load conditions. Let's delve into the concept of thrashing. Picture this. A system is constantly swapping pages in and out of memory. The rate of page faults is sky high, and the system's performance takes a nosedive. This phenomenon is known as thrashing. Now, a well-chosen page replacement algorithm can be the knight in shining armor, stepping in to reduce unnecessary page faults and mitigate the effects of thrashing. Page replacement algorithms are like the gears in a well-oiled machine. If they're not working in harmony, the machine grinds to a halt. Similarly, if these algorithms aren't optimized, the system can become bogged down, resulting in a sluggish and inefficient performance. Now, let's talk about how we evaluate these algorithms. The key metric is the total number of page faults. It's a simple principle: the fewer page faults, the better the performance. Each page fault represents a moment when the system had to pause, retrieve a page from disk, and potentially swap out another page to make room. Each of these operations takes time and slows down the system. Different algorithms have their strengths and weaknesses in various scenarios. For instance, the first in, first out method is simple, but can suffer from Beladie's anomaly. The least recently used approach is more sophisticated, reducing page faults by prioritizing recently used pages, but it requires tracking the age of each page, which adds complexity. On the other hand, the optimal page replacement algorithm is theoretically the best, but it's not feasible for real-time systems. The clock technique offers a practical compromise, while random replacement, as its name suggests, replaces a random page. Choosing the right algorithm is crucial for optimizing memory use and improving system performance. It's like picking the right tool for the job. The end result depends heavily on your choice. So that was a quick tour of page replacement algorithms in operating systems. We've journeyed through the simple yet sometimes problematic FIFO method to the more sophisticated LRU approach that pays attention to recent page usage. We've explored the theoretical perfection of the optimal algorithm and the practical efficiency of the clock method. And let's not forget the wild card of the bunch, the random replacement algorithm, which can surprise us with its effectiveness. We've also highlighted the significant impact these algorithms have on an operating system's performance. Remember, a good algorithm can prevent the dreaded thrashing and keep the number of page faults to a minimum. These algorithms are the unsung heroes, quietly working in the background, making sure our computers can multitask smoothly. Remember, effective page replacement is key to your computer's multitasking magic. Thanks for watching, and stay tuned for more discussions on the intriguing world of operating systems.